if A is an m by n matrix, then we do have a very cheap way of computing a norm of A. It's the same thing as having an mn by 1 vector, right? So if I had the matrix 3, 2, 7, 4, 0, 1, we could just as easily consider that to be like the vector 3, 2, 7, 4, 0, 1. And then we could apply a vector norm. So the only case where this is sometimes useful is what we call the Frobenius norm of a matrix, where we take the 2 norm of that vector representation. So in other words, it's the square root of the sum of the squares of all the elements of the matrix. So the Frobenius norm does come in handy sometimes, but it turns out to be not the most useful idea for matrix norms. The one that we do use looks stranger and more complicated, but it has some particularly important advantages. So here's a definition of the matrix norm. The matrix norm of A is the maximum over all unit vectors of the norm of A times X. This is often called an induced matrix norm because it's induced by a vector norm. You see, X and AX are both vectors, so if you have a vector norm, then that defines a matrix norm. So that means we can talk about the 2 norm of a matrix, the 1 norm of a matrix, and the infinity norm of a matrix. If we want to visualize what this norm is telling us, it's about the actions of A as a linear transformation. So let's take the infinity norm as an example. Remember that the unit circle in the infinity norm is actually this square. With corners at 1, 1, and so on. Well, if these are the vectors, then after we apply A to every single vector in that picture, what do we get? Well, each of those 4 corners will map somewhere. And it's not hard to show that straight lines will have to map to straight lines under a linear map. So we'll get a parallelogram. Then the infinity norm of that parallelogram is the part that sticks out the most in some direction. So in this case it would be the y-coordinate of these points in absolute value. Okay, so it's all about the action of A applied to all the different vectors on the unit circle in whatever norm you've picked. There's another way of defining this. So instead of just looking at the maximum over unit vectors, we can look at the maximum over all vectors except for 0 of the ratio of norm AX to norm X. And the reason that we can do this is because the norm of alpha X, if alpha is a scalar, remember, is alpha times the norm of X. And the norm of A times alpha X, well, that's just the norm of alpha times AX, because alpha is a scalar. And by the properties of norms, that's absolute value of alpha times the norm of AX. And so what that means is if we take a ratio of the norm of A times alpha X over the norm of alpha X, the alphas cancel out completely. So we could rescale the vectors that we're considering to be any particular norm. So the unit norm seems the most useful. So for instance, if you think about the 2 norm picture, right, what we're saying is that there's a unit circle, of course. We might pick vectors on some other circle, say out here. But in fact, in terms of this ratio norm AX over norm of X, we get the same result for every vector on an array like this. It doesn't matter what the norm of X is, it cancels out of the ratio. Okay, so we have these two definitions that we can use now for the matrix norm. And there are two main properties that we're after by using this norm that come in these next two theorems. So we're going to spend just a few minutes on these theorems. The first is that the norm of AX is less than or equal to the norm of A times the norm of X for all vectors X. Well, this turns out to be incredibly simple, right? By definition, the norm of A is the maximum over all non-zero vectors of norm of AX divided by norm of X. So if you take the maximum over a whole set, right, that's greater than or equal to any particular member of that set. Right, that's what it means to take a max. And so therefore, you have the norm of A. So therefore, the norm of A is greater than or equal to norm of AX divided by norm of X. And that rearranges into the statement of the theorem. So that turns out to be just playing a game with the definition of matrix norm. The slightly beefier result, which is also extremely useful to us, is that for any two matrices A and B, the norm of the product AB is less than or equal to the product of the norms, norm A times norm B. Norm of a product less than or equal to the product of the norms. Now, when I say all matrices, of course, I'm saying when the product A times B is defined. That's implied here. So let's prove this statement. By definition, the norm of AB is the maximum over all non-zero vectors of the norm of ABX divided by the norm of X. Well, we can think of ABX, we can use the associative law to write it as A times the vector BX. Well, by the previous theorem, we're going to rewrite norm of A times BX as less than or equal to the norm of A times the norm of the vector BX. Well, by the previous theorem again, applied now to the vector BX, we can replace BX with a less than or equal to norm B, norm X. Now we have norm X in the denominator. It cancels out. Now we're taking the maximum over all the different possible X of the quantity of the quantity AB. So the maximum over non-zero X of the quantity norm A, norm B. Well, there's no dependence on X at all, so the maximum is just the product of the norms. And so since we started with norm AB, we showed all the way that it's less than or equal to norm A times norm B. We're done. So it's really, backing up for a second, it's really these two inequalities that make induced norms so useful to us. And we'll be seeing that very shortly. Before we finish, it's worth pointing out that, from the definition, it's a big headache to have to compute what the norm of any particular matrix is. That's the downside of an induced matrix norm. But for two of our very popular norms, it turns out to be incredibly easy. So there's a way of applying the definition so that we get a formula for the norm of a matrix. And they're quite similar, but they have an important difference, so you have to pay attention to the details here. So the one norm of a matrix A is the maximum over all columns for the sum of entries in each column. So there you can see there's a mistake here. This sum should be over M. So it's an M by N matrix. So there are M rows. Okay? So what this means is that you take the row sums of the matrix. I'm sorry, I said it wrong. You take the column sums in this matrix and then take a max. The infinity norm, okay, is the maximum over each row of the sums across columns. So we take row sums, we sum across the columns of the matrix, and then we take a max of that set. So one way of remembering this, it's kind of goofy, but the 1 in the subscript here is vertical, and the sums go vertically. The infinity kind of sits horizontally, and the sums go horizontally here. Okay, so that's just a little memory device. For example, for this particular matrix A, if we take the one norm of the matrix, it's the maximum of the column sums. Remember to take absolute values before you start adding. So the first column is 3, the second column is 6, the third column is also 6. So the answer here is 6. The infinity norm of A is the maximum row sum. So we sum the rows, again after taking absolute values. First row gives us 6. Second row gives us 5. The third row gives us 4. So in this case the answer is 6 again. Although for other matrices the answers are different. Now, it's probably occurred to you by now that the most natural vector norm to work with a lot of the time is the 2 norm. That gives us the ordinary kind of distance that we're used to, the ordinary kind of circles that we're used to, and so on. But I haven't said anything about computing the matrix 2 norm from a formula. And the truth is that there is no, in parentheses, easy formula for the 2 norm of a matrix. It turns out that there is a formula, but it takes a computer to compute it.